In the last video, we introduced this idea of the derivative of a vector function, and we saw this big scary limit that was reminiscent of things we had seen back in Calc 1. And we'd really like to try to quickly develop a cool shortcut for how I could calculate the derivative of a vector function without always having to go to this big scary limit definition. So let's take a look here at this first theorem. Here's what it says. If it's the case that you have a vector function with component functions of f, g, and h, as long as those component functions are differentiable functions, like good old classic Calc 1 differentiable functions, then it must be the case that the derivative of the vector function, here it is, this is our first beautiful shortcut, is just take the derivative of each of the component pieces. Okay, so notice this is really similar to what happened with limits of vector functions. To do the limit of the r of t, I just did the limit of each of the three inner functions. And it's apparently now the same thing with derivatives. It's an awesome, convenient way of transforming a Calc 3 question into kind of three individual Calc 1 questions. But how do I know that this works, right? Like, I mean, it would be really cool if it works this way, but how can I be sure? We're going to go ahead and attempt to justify that here by writing out a proof. So let's go ahead and take a look at what would happen. How could I know that this is the derivative if all I had to start with was this is my vector function and the component functions were differentiable? Okay, so let's see. So I'm going to go ahead and start off by saying that we're going to go ahead and use the starting definition for r prime of t. So I'll say using the definition of r prime of t, we would calculate the following. We would say, shift this down a little bit, but we would say r prime of t, the only way that we have to calculate it right now is to use a big scary limit. Now, typically, we saw that limit with a limit as h went to 0, but I'm actually going to use a different letter than h because I'm already using h up here, and I don't want the h's to be confusing. So instead of h, how about we use something like a k? It's still going to be the same exact basic setup. It'll just be t plus k instead of t plus h. And you'll see that I'll still have k going to 0, much like I would have had h going to 0. Okay, so this is what I have to start with. I need to figure out how can I get from here to this cool shortcut. So I'm going to go ahead and manipulate the limit a little bit. First off, I think one of the things that we could do here is we could rewrite this actually. We could go ahead and say, I'm going to take this 1 over k that's here. I'm just going to pull that off to the side. And then I'm going to go ahead and think about expressing my two vectors here. First off, this vector, r of t plus k, is pretty easy to express. That would just be f of t plus k, g of t plus k, and h of t plus k. Right? Because that's just my vector r when I go and replace all t's with t plus k's. Now, of course, I want to subtract from this my vector r of t. So my r of t vector just looks like f of t, g of t, h of t. Okay, so I haven't really done anything except just fill in some of the pieces that I already had. Okay, but what I can do now is actually think about doing this vector subtraction over here. Okay, what if I completed this vector subtraction and wrote the inside of those brackets as just a single vector? Well, I still have my 1 over k on the outside, but now I would have a vector with first component of f of t plus k minus f of t. That would be the first component, right, when I do the subtraction here between the vectors. My second component would be the g of t plus k minus g of t. And my final component would be the h of t plus k minus h of t. And this is the one big vector that I have. The cool thing though now is actually I could take this 1 over k if I wanted and say, wait, 1 over k, that's just like a number. So if I just have now a number times one single giant vector, I could just take that number and multiply it to each of the individual components. This is just like what we did back in one of the very first sections. So if I want to, I could go ahead and re-express this again as now just the limit of one giant vector. It's my f of t plus k minus my f of t all over k, my g of t plus k minus g of t also all over k, and my h of t plus k minus h of t all over k. Okay, so I've transformed the initial limit so far into this. Whatever the derivative is, it's equal to this thing. Okay, but here's something really cool. What did we just show a few videos back about what you can do if you want to take the limit of a vector function? Well, we said that would actually be the same thing as just applying the limit to each of the pieces within that vector function. So I could just do the limit of the first piece, like I have here, and then just kind of rinse and repeat for each of the other components. Now, as you're writing this down, you can start to think about where in the world might I be able to go from here, because now I have 3 individual Calc 1 style limits. But even more than that, I think these limits are actually, well, pretty recognizable. I think we even talked about them in the last video. Doesn't this limit right here, take the first component, doesn't that look unbelievably similar to this limit right here? I mean, go back and forth between those. The only difference here is that instead of a t, we have an x, and instead of an h, we were using a k. But like, we have the exact same basic structure. And it's the same thing over here, except we're just dealing with a different function. And same thing over here, we're just dealing again with a different function called h. So actually, these are 3 basic Calc 1 limits. And since I know that my functions, the f, the g, and the h, are differentiable, then what that means, say here, since f, g, and h are differentiable, then I know all 3 of these limits must exist. So these 3 limits must exist. And more than that, I know based on Calc 1 what they have to be. They're the derivative limits. So they should be f prime, g prime, and h prime, respectively. So that means that I'm going to be left here with f prime of t, g prime of t, and h prime of t. That is freaking awesome. That means that calculating the derivative of a vector function is actually so easy. It's, again, 3 simple Calc 1 derivatives. Okay. Notice, though, in this proof, there was actually nothing special about the vectors needing to have 3 components. We were thinking of them with 3 components, but they could have really had any number of components. And so actually, this proof works for vectors no matter how many components they end up having. So in the videos to come, we'll take a look at how we can take derivatives of some vector functions, build some tangent lines, and do a lot of similar sorts of things that we did in a Calc 1 class with derivatives.